Hello everyone, welcome back. We've been talking about extended bond rule, and I have mentioned it a couple of times that this is the idea when you're dealing with multiple qubit systems. We will now precisely work out an example. So let's say if I have a k qubit system, then the basis element, uh, let's say beta is the basis. This is a beta is a set of orthonormal states labeled by k-bit strings. All right, so if I have a 2-qubit system, then these are the strings, right? 0 0 and 0 1, 1 0 and 1 1. These are the strings that they are trying to mention. So for k qubits, you will have k 0 or 1s here, right? So let's work out an example. Let's say I have a 3-qubit system. Okay, so if you have a 3-qubit system, then let's say that I have this state phi, which is equal to I by 2 3 zeros, because this is the basis of a computational basis of 3-qubit system, right? And if you remember correctly, then this is nothing but 0 tensor 0 tensor 0. So this is just a notation, shorthand notation. All right, so then this 12 plus 5i by 26 0 0 1. So as the coefficients can be in general complex numbers, so you can see that it is true here as well. All right, half, then you have 1 0 1 plus 3 by 10 1 1 0 minus 2i by 5 triple 1. All right, so this is a valid 3-qubit system, and this is a valid state of a 3-qubit system, and you can check that it is normalized. I don't want to do that calculation. You can check it by yourself. Now let's say that I perform a measurement in the first qubit. Okay, I perform a measurement in the first qubit, and I get 1 in the first. Okay, let me write it properly. I get 1 in that qubit. Okay, so what do I have to do? If you look at this state, then if I get 1, my new state will be, if you remember the Bourne's rule, then this would be 1 on the first qubit inner product with phi, right? And that was nothing but whatever you have left whenever you have this 1s here, right, in the first qubit. So you will get all these 3 terms with because when you take this inner product, these are the terms only that survive, right? So this inner product will be minus half 0 1 plus 3 by 10 1 0 minus 2i by 5 1 1. All right, But as you can see, obviously this is not normalized, right? So this is not my collapse state. So what will be my collapse state? My collapse state, and let's give this a name. Let's call this alpha. Okay, so this collapse state is not normalized, so I have to normalize it by its norm. So what I have to do is I have to take the norm of half. Let's check that. Then that would be, these are orthonormal bases. So the norm of this would be nothing but minus half square plus 3 by 10 square plus minus 2y by 5 times 2y by 5, right? And if you sum them up, what you'll get is nothing but half. So this is not normalized, because by normalized I mean that its norm is 1. So what do I have to do? My collapse state will be alpha divided by the square root of a dot a, as I was mentioning in the last video. So it was something like this, right? So it should be square root over 2o. And okay, my collapse state, okay, let's see. My collapse state will be 1 in the first basis inner product of this, tensor product of this. I'm sorry, that was the wrong word. Not inner product, but tensor product. Okay, so that would be nothing but 1 tensor, and if you calculate it, it will be square root of 2 alpha. All right, so this is my new state, and what was the probability of getting 1 in the first qubit? That is nothing but the norm of this state, which is half. So before measurement, we can, if we know the state, we can say that if we do a measurement, the probability of getting 1 in the first qubit is half, and that is what was said explicitly in the Born's rule. So what's the idea? Whenever you have a multiple qubit state like this, what is the probability of getting let's say 0 in the second qubit? Then what you'll do, you'll take these, this and this, these three elements, remove that 0, and whatever you have, write that, and the norm of that vector will be the probability, I mean the inner product of that vector with itself will be the probability of getting 0 in the second qubit, and your new state will be a normal will be normalized in this way. All right, so you will work out some examples in the quizzes after this video, and I hope then it will be clear. And whenever we will be focusing on quantum algorithms, we will do measurements on one of the qubits and then try to handle those things. All right, and those will be very important when we are designing quantum circuits and trying to solve real life problems. All right, so I hope it is clear to you. Otherwise, please ask me during the live discussions. I hope it will be clear to you. All right, thank you.